Now we're going to determine how to calculate atomic mass for an element. Atomic mass is just the average mass for a naturally occurring element, and we have to calculate an average mass because we have naturally occurring isotopes. These isotopes have different number of neutrons and therefore a different weight or mass. So if we had a natural sample of an element, we need to account for that. So the way we get the atomic mass is we essentially just take a weighted average of all of my isotopes. We figure out what fraction of my isotopes, or what fraction of the sample is from that isotope right here, and then we figure out the mass of that isotope. So we multiply the fraction times the mass for each isotope, and then this symbol just means sum. So then we add them up for all of my isotopes. So if we want to write that in a longer fashion, it would look like this, but notice I end with dot, dot, dot. If you had 7 isotopes, you would do this for all 7 isotopes. But really easy, fraction times mass, and then you add up for each isotope. If you're given a natural abundance in a percentage, you just have to do that percentage over 100 to figure out what your fraction is. And you can check that you did the answer correctly, or you calculated the correct answer, because that atomic mass should be listed below an element symbol in the periodic table, and you can check to make sure that it matches. Alternatively, you can use your calculated atomic mass to actually figure out what element you have by matching it to an element who has that number below it on the periodic table. So let's look at an example. Let's say we have an element with 3 naturally occurring isotopes, and it gives us the mass and natural abundance for all 3 of these. So what I like to do, here's our equation, is just go ahead and look at all 3 of these one at a time and list their fraction and their mass and show how they're going to be multiplied together. So isotope 1 has a natural abundance of 90.48, so for the fraction, I just do 90.48 over 100. That's going to give me my fraction, and I'm going to multiply that by its mass, which is 19.9924 AMU. So that's this isotope 1. Now I'm going to do the same thing for isotope 2. So for isotope 2, his abundance is 0.27%, so I just put that over 100, and then I multiply it times his mass, which for isotope 2 is 20.9938 AMU. All right, isotope 3. Notice that isotope 3 does not list a natural abundance, so it might seem like you're missing some information. However, since these are all percentages, we know that my percentages all have to add up to 100%. So if I want the percentage of the last one, I just subtract these two from 100. So I have 100% total, and if I take away 90.48, and I also take away the 0.27, I subtract those, I'm going to get 9.25. So that must be the natural abundance of my third isotope. 9 there, 9.25, and so I put that over 100. So just keep in mind these percentages have to add up to 100. If you're missing one, you can figure it out from the others. So I do that, and again I multiply it by 21.991 AMU, which is his mass. And now all I do is add these 3 pieces together. So I can punch this into my calculator, 90.48 over 100 times the mass, and then add the second component and add the third. So this is for isotope 1, isotope 2, isotope 3, and we just need to add them all together. That's it. So when I do that, I add all of these pieces together, I get that my atomic mass is equal to 20.17998 AMU, and I can go back and I can track my sig figs by looking at how many decimal places I have in each one. So I should stop there, and so I'm going to get 20.18 AMU. I don't agonize over the sig figs on these. What we want to do, if we look back at our problem, is we want to use this, we want to find the atomic mass, and we want to, by comparison, identify what element this is. So the sig figs aren't going to be the end of the world, because no matter what, it should be very, very close to something on the periodic table. So now that we have my atomic mass as being 20.18 AMU, make sure to leave the units there, I'm just going to look at the periodic table. And if we look, neon has an atomic mass that is nearly identical to this. So my element must be neon based on the atomic mass. If you get a number that's not close to anything on the periodic table, you probably made a calculation error somewhere up here, and you just need to go back and double check. But overall, these problems are really, really simple. You just do fraction times mass for all your isotopes, doesn't matter how many you have, and then add those guys up. That's it.